I think we can start. Thank
Okay.
you for Dr. Shea today. So I'd like Vince to introduce our speaker. Thank you.
All right. Our speaker today is Dr. Lei Jie. He's Professor, Chancellor's EDGES Fellow and Presidential Impact Fellow in the Department of Electrical and Computer Engineering at Texas A&M, and also the Associate Director of Energy Digitization at Texas A&M Energy Institute. He received his bachelor's in electrical engineering from Tsinghua University in 2004, his master's in engineering science from Harvard in 2005, and his PhD in electrical and computer engineering from Carnegie Mellon in 2009. So that's a resume. His industry experience includes ISO New England and Edison Mission Energy Marketing and Trading. His research interests include modeling, control, and data-rich large-scale systems, grid integration of clean energy resources, and electricity markets. Thank you for coming.
Thank you. Let me share my screen. Great pleasure and honor to be presenting at the CURENT seminar series. Thank you, Professor Chen, for the kind invitation. CURENT has always been a center of excellence in power systems across the country and across the world. So it's a great honor to be presenting at CURENT. I've also had a lot of working collaborations with various different faculty and students at CURENT, so it's a great pleasure. What I'll be talking about today is some work that we have been doing over the past 2 years, primarily starting from just about this time, 2020. And it sort of gave us some food for thought regarding how we might think about future extreme events on the electricity sector and how that might change the way we do some research, in particular at the intersection of engineering and public policy. And I wish to thank a large group of collaborators, particular students and postdocs who has been with us throughout in conducting this research. So the key word here is really cross-domain and open data-driven approaches. So I'll first briefly talk about the general trends that I see as regarding the electricity sector. And then I'm going to talk about why we should care more and more about extreme events. And then we'll give two particular case study with some in-depth analysis. One on the impact of COVID on the electricity sector, more on the short term. And the other one is more regarding to something that happened close to my home in Texas. And we'll try to draw some common themes in both case studies and suggest some concluding remarks. And so I think this is how I personally think about a problem. If you think about the largest greenhouse gas emission by sectors, in the US and in most of the developed nations, it is always transportation and electricity being the top two. So anyone who wants to combat climate problems, you have to deal with the top two sectors, right? So how do we deal with these top two sectors? There seems to be some common agreed upon path. When you ask anybody on the street these days, people can talk about that. It seems like the common viewpoint these days is that in order to combat these emission problems and climate problems, number one, we need to decarbonize the electricity generation, right? Make the electricity generation as clean as possible, right? Replace a lot of the fossil fuel with cleaner resources such as wind and solar. And then number two, let's burn all the cars not on gasoline, but on electrons. Because if the electrons are coming from cleaner resources, then presumably you sort of take care of the transportation sector emission as well. So that seems to be the common agreed upon path these days. And my question to the audience here and also to myself is the grid infrastructure really ready for that kind of ambitious transition? And my humble opinion is that it is far from being ready. A lot of things that need to be done to make that happen. And as a matter of fact, we actually wrote about this in an article that appeared last summer in June with some colleagues at MIT and Berkeley, basically articulating what are the missing pieces and what are some of the key priority areas that one should look into as far as enabling carbon neutral transition on both electricity sector and transportation sector in terms of the grid. And we also have published a companion op-ed piece, opinions piece at The Hill. If you look at the date, it's actually before the approval of the infrastructure bill that a lot of people are talking about these days. So we were trying to do some outreach to the public policy aspect as well. And this is sort of just to give you some high level view of how we think about a research as far as the future energy system is concerned. This is really how we think about it, right? Fundamentally, we are technologists. I think most of you are also technologists, experts in power systems or power electronics. So we ought to start from something on technology. Right? Here we draw upon most of the technological innovations from power electronics, from data, from machine learning. But we can't stop there. You have to also make a conscious effort to articulate the value proposition in terms of the business, in terms of economics, in terms of the data analytics of this technological innovations. And even that is not enough, given that it's a heavily regulation coupled industry. One has to make extra effort to translate all this into the policymakers' arena. And here's some samples of work that we have been doing along those lines. So this is sort of how we are thinking about the grid problems moving forward. So a lot of our specific research challenges, I think, for the graduate students who are in the audience here. Let me just name a few of them. For example, how do we make sure that when we have massive level, edge level devices such as solar, electric vehicles, and so on, how do we make sure the cyber as well as the physical security is certified? How do you design a market and procurement of flexibilities in a carbon neutral power systems, which is likely to have many more fluctuations, and therefore we need much more procurement and a market construct for flexibility. And then perhaps more importantly, how do we plan a coupled infrastructure for extreme events, such as extreme weather and such as extreme weather conditions, and something totally unexpected, such as COVID. So today I'm going to be focusing on the discussion on this bullet point. And I'll give you two particular case studies, one on COVID-19's impact on the electricity sector, the other one on how to go about analyzing the winter storm in 2021 in Texas. I would like to convey that there are some common themes that support and underline this kind of a work, and that is a sort of an open cross-domain data-driven framework that traditionally we might have not been thinking along those lines in traditional power systems planning studies. So that might be something we ought to be focusing more in the future, okay? So let's start from the impact of COVID. So this is just about 2 years mark when we started this piece of work. And Professor Chen was actually also a great source of inspiration back then, because I know she was also looking quite a bit into the energy burden and the social justice issues associated with COVID. But here we are sort of taking more of a electricity sector focused approach. And it really thanks to some of the data set that my student discovered at the onset of the COVID, which is something that is quite visual. I believe we human beings are extremely visual species. So this is the NASA nighttime light data. So this is the city of New York, in particular in the Manhattan area, and we have picked two particular days both are in, one is before the COVID hit, and the second one is right after COVID hit, when New York City was the pandemic's epicenter. And then we use the signal processing to get rid of the ambient lighting situation. So these are sort of a midnight time for the same location, same day of the week, just before and during COVID onset. And I was literally shocked when I first saw these pictures, because it basically suggested, if you can just use your eyeball to see the differences. It basically suggested on these two, nights, one before, one during COVID, the brightness of the city was dimmed down by almost 40%, right? So that came in as a shock, because one could, think about what is determining this kind of a brightness. It really was because, it's really the human-driven activities, right? It's commercial buildings and lighting and so on and so forth. So that is a very visual and direct indication that COVID is affecting people, and therefore is affecting the electricity consumption, and therefore affecting the electricity sector. So that was sort of a motivating picture that really got us thinking about what exactly is going on, and how could we analyze at least the short-term effect of COVID on the electricity sector. So we took a bit more efforts, and this is a sort of a viewing the pandemic through the electricity consumption perspective. As you could see that this is showing the New York ISO's demand reduction rate. So be careful, the y-axis here is the demand reduction rate compared to counterfactual baselines. And you could see there is a sizable differences, as high as on the order of 10s and 15%, right? So this is sort of a another perspective of us feeling that, okay, this COVID really has some significant impact, at least in the short run, on the electricity consumption. So then we kind of dig a little bit deeper and then say, how could we help? How could we help the community? And one thing that we felt that perhaps we could offer some help is to sort of go beyond traditional electricity-centric view of what happened during this period, and perhaps add an open and cross-domain data hub that would not only help us, internal groups to figure out what happened, and also to help, the community at large on what happened during this period. And that was the starting of this COVID EMDA data hub, which everybody are more than welcome to go and check it out and use as you need it. It's a completely open approach. And so what is sort of unique about this is that it goes beyond just the usual suspect of electricity sector data. It goes including things that we would probably have never included in the past when it comes to electricity planning. For example, we would have included the public health data from Johns Hopkins databases. We would have included mobility data from a group called SafeGraph. We would also have included the nighttime image data from this NASA's NTL dataset. So it gave us a sort of a starting point to begin to reason about what happened during this short run effect of COVID on the electricity sector, and then what might be some of the possible indicators that might be most indicative of what happened. And it also has attracted some attention in the news article and so on. And also we have a couple of papers that is published based on that. So let's get down to the bottom of it and how, share with you how we, analyzed it. So the first thing that we would like to quantitatively analyze is that what exactly is the COVID impact on the short run, on the electricity sector, right? So that seems to be a straightforward question. perhaps a naive approach would have been that you just look at the electricity consumption, let's say at the onset of a COVID period, March, April of 2020, and then you compare against the same location a year ago or 2 years ago, and then you subtract the difference and you call that as the impact of COVID on the electricity sector. Is that a good approach? I would argue that it might not be the best approach, because if you just simply use the previous year or previous 2 years of data and subtract from the data at the onset of COVID, there's a lot of ambient differences. For instance, the weather conditions, economic productivity conditions, and other conditions. So it would have not been a fair attribution to the impact by just subtracting the consumption from 2020 level to the 2019 level and so on. Instead, one should perhaps think about what the economists call it counterfactual, right? Or a lot of engineers, we call it a baseline, right? So one has to first establish the so-called baseline model, which is the following question: if it weren't for COVID, what would have been the electricity consumption in New York City in April 2020, right? That would be a hypothetical counterfactual data of electricity consumption during the onset of that period. And then you compare with the actual consumption during the same period. And that would have been a fair attribution of COVID impact on the electricity sector, right? So I hope everybody get that point, especially for our students here. And that really is the guiding way of thinking about any major impact on the variable of interest. So then the next question is, of course, how do we establish these counterfactual models? And here the model is described in detail in this paper, but here I'll just briefly mention that it is based upon a deep neural net-based ensemble backcast model. And we utilize the onset of January and February of 2020 as the validation period, because right before, if you recall what happened in 2020, right before March, things were still relatively normal. So we used that first 2 months of 2020 as the validation period. And then we try to calibrate the model so that it does capture the baseline quite well. And then we ran the model for middle of March until end of April, and use that period as the period to construct the counterfactual and compare that with the actual consumption, extract that difference, and try to use some further analysis to figure out what exactly is the most indicative factors, and is there any interesting insights. So that's the key idea. And here are some first high-level finding as far as the impact of on the electricity consumption is concerned. So on the top table, these are the percentage of drop at the regional transmission organization level, RTO level. As you can see, there are California, Midwest, New England, New York, PJM, Southwest, and Texas. And then on the bottom table are some of the most severely impacted metropolitan areas. So as you could see, New York City was hit particularly badly, right? And Boston was also quite severely affected as far as the electricity consumption is concerned. So that's sort of the first interesting discovery. But then, if you dig a little bit deeper, and then you might say, okay, how do we explain those changes? We might not be able to do some causation, but at least could we try to come up with some good indicators that might have been a good indication of such changes, so that we could help, at least in the short run, for the policymakers, for them to plan for, at that time, you recall, the big topic was about reopening the economy, right? So how could we, as you gradually reopening the economy, what would have been the impact as far as electricity consumption is concerned. So that was something we were hoping to help, okay? So we turned to something that was rather unusual, sort of a data sets in terms of understanding electricity. We turned to this SafeGraph data set, which is actually something that captures the mobile devices in the USA. So we got some 30 million mobile device data in the US. And here is just some animation on, what exactly does so-called social distancing. Everybody was talking about social distancing, if you recall what happened 2 years ago, right? What exactly does that actually mean when it comes to a mobile device, which indicates the location information of device holder of people, and percentage of them who were completely staying at home. So it's a sort of an animation of different time period during the first pandemic wave. And this is sort of the average stay home rate. So as you could see, as time projects from the early February towards early April, there is a color change from more towards the blue side towards the more of the red side, which means that there's a increasing percentage of population staying at home completely. And that was, captured to many of us, our personal experience as well. And then here are just some snapshots that give you maybe a better feeling about what happened as a country in terms of social distancing patterns. So as you could see, the country is moving more and more towards a completely stay-at-home rate, which is quite a remarkable public policy intervention if you think about it, right? And so the next question is, how do we possibly use all this different data to provide a bit more reasoning? We might not be able to say causation, but at least we might be able to suggest what are some of the indicators that might have been very effective in indicating the change of electricity consumptions, right? So here, we're just listing a bunch of data visualization that we have collected, and just to kind of give you some feeling about some of these data sets. Here, everything is still kind of a qualitative, but we would like to go a bit more quantitative moving forward. But here, I want to stop for a minute and just share with you a couple of interesting observations. One is that if you refer to this idea of social distancing, everybody was talking about that at the time. But if you look into the data, the social distancing actually has very different connotations when it comes to different kinds of intervention or policy construct. For example, I would like you to focus on the difference between the third one and the fourth one on this table. The third one is population of on-site workers. And then the fourth one is the mobility in the retail sector, meaning how many people actually go shop at your local grocery stores and your shopping malls and things like that. As you could see, the population of on-site workers had a almost average behavior all the way until the week of March 15th. And then there is a very abrupt change. Do you recall what happened on March 15, 2020? That was when the White House declared a national emergency. So there was a very you can see there's a very visible abrupt change in terms of the population of on-site workers, because it's a top-down decision for this on-site worker. Whereas if you contrast that with the mobility in the retail sector, meaning how many people go to the shopping malls and how many people go and physically buy things from the grocery stores, as early as mid-February, you can already see some slowly but more kind of a less abrupt drop of traffic towards the retail sector. That suggested that people are already kind of making their decisions on their own of reducing their visits to these retail sectors as early as mid-February and so on. And then there is a gradual reduction because these are more of a bottom-up indicators of social distancing, right? So that's, so even though we were talking about the same concept of social distancing, it has very, very different connotations when it comes to top-down policy versus bottom-up individual responses. And that was something interesting to observe. So then let's get to a bit more quantitative side of things. So the question that we would like to ask is, could we think of a set of variables? We have a number of different data sets here. Then the question is, could we think of some indicators from this very different sets of variables, and then try to prioritize them, and then figure out which one would be the one that would be most indicative of the change of the electricity consumption during this period. And therefore, we could use that as one of the variables to pay attention to when it comes to making decisions for reopening and so on. But then here, the fundamental challenge that one might face is that even though we have all these different sets of data sets, they are not necessarily independent of each other, right? So for example, social distancing, they're not completely independent of COVID cases. And they're not necessarily independent of the shutdown of the retail sectors. So the research question is really about how do you utilize a linear interdependent set of time series data, and then try to prioritize their impact on a particular variable of interest, in this case, the electricity consumption variable, all right? So that's really the question that we're posing. And then we draw upon a lot of pioneering work from the economics, in particular macroeconomics literature. Professor Christopher Thims, who was the one that really pushed this a lot in the macroeconomics area. He's a Nobel laureate from Princeton. And this is the idea that actually a lot of engineers might be quite familiar to these concepts of utilizing these multivariate stochastic processes to delineate such interdependent time series data's impact on a particular variable of interest. So without getting too much into the math side, but let me show you the result of what we have found. And this is basically the so-called variance decomposition, meaning we're trying to decompose each of the variables' impact on the electricity consumption reduction. All right, so we are putting here New York City and Houston as two examples of that. So as you could see in the case of New York City, the mobility in the retail sector seems to be a fairly important indicator on explaining such changes on the electricity consumption, right? Whereas in the case of Houston, you might see that it seems like the stay-home population seems to be a more of a dominant factor when it comes to explaining the change of behavior in electricity sector. So that's kind of interesting. If you think about it, that actually is something that might be worth reason about, because in the case of New York, it's a much more concentrated commercial centric area. So the foot traffic to the retail sector will be a strong indicator on the business and activities, therefore on the electricity consumption. Whereas if you've ever been to Houston, you know that Houston is a much more spread out city. You need to drive from point A to point B pretty much anywhere. And people have big houses and big air conditioning. So stay-home population would have been a major indicator on the change of electricity consumption. And not only you could do this kind of analysis, you could also do some what-if analysis. For example, engineers, we like to do so-called sensitivity analysis, right? In the policy arena, you would like to figure out, what if there is a 1% increase on the daily new cases, or if there is a reduction on the mobility to the retail sector, how would that affect the electricity consumption in that area that you care about, right? So using this framework, you can also do this type of what-if scenario analysis. Essentially, putting into engineers' jargon, it's almost like studying the transfer function. Between a variable of input here is a particular policy intervention or change of behavior, and the output will be the electricity consumption changes, okay? So this is the part that we'd like to summarize. At the onset of the COVID in 2020, we, spent quite a bit of efforts trying to build up this data hub that is cross-domain and open access. The goal is to try to understand the short-run impact of COVID on the electricity sector. And it seems like mobility in the retail sector is a particularly strong influencing factor. And then many more, research could be conducted based on this type of open cross-domain approaches when it comes to planning for the future. So just as we thought we were out of COVID, another major event hit the power grid, and that was the February 2021 Texas power outage. The sad fact is that there are more than 200 people died because of this, and economic loss was also tremendous. And you could see that again from the nighttime image data. Here is in the city of Houston, just 10 days apart. You could see there's a substantial change of brightness because of this winter outage. While people were still talking a lot about it, at the time, we were thinking, how could we help? How could academics help? While there are going to be serious, very detailed, closed-door investigation from the regulation bodies and NERC and other agencies, we thought at least there's a need for the broader research community to at least understand in terms of what happened to the best that we can, and then perhaps trying to understand what could have been done differently, or what are some of the possible corrective measures that one could begin to think about. Because there was a lot of finger pointing and different opinions, but we thought as academics we could at least try to provide a bit of a model-based and simulation-based quantitative analysis of what happened and what could have been done differently. And for anyone who is working in the power industry, you might heard about something called a CEII, Critical Energy Infrastructure Information. In other words, a lot of the power network is subject to the CEII protection under the Energy Act of 2007. Therefore, one could really not conduct a full-blown simulation based upon the actual grid model, but thanks to many colleagues, in particular my colleague, Professor Tom Overby, there's been a lot of development in the research community on developing open synthetic grid that looks just as realistic as the actual grid, but then it could be a great resource for the researchers to understand some of the large-scale issues. And then we, in this particular piece of work, we built upon a synthetic Texas grid model that was created by my colleagues, and then we further calibrated that to match what happened in that particular event on that week of February 15th, 2021. And then we carefully calibrated according to all the publicly available information from generation composition, demand distribution, and transmission network data. And then the result is quite closely matched with the actual published records. So let me show you some of the calibration we did. The first thing we did was we tried to calibrate the synthetic model with the actual load and load forecast and generation output data from the public resources. And then we come up with the wind and solar counterfactual forecast. So as you could see that at the onset during this period of the event from February 15 until February 17-ish, the actual and the estimated generation capacity is quite closely matched with each other to the best we can. And here is another calibration example that we did. We try to calibrate the actual and counterfactual generation of wind as well as solar generation. So as you could see, the calibration was quite well matched all the way until around February the 9th. And then these two models became quite far apart. And the reason it became quite far apart was because this counterfactual model could not capture some of the winterization effect on the wind turbine solar panels. If you only use wind speed and irradiance, that would have not been able to capture it. So that's why you see there's some discrepancies over there, which also suggested that there are other weather-related outages on these two generation sources, just as all the other sources of generation. And then we try to mimic what happened in terms of the generation and grid operating point. And here we try to use the reproducing of the optimal power flow as a way of calibrating and determining the amount of load shedding necessary for the grid operator. We first create a counterfactual demand and renewable generation based upon the hourly data. And when we try to follow the event log to derate or disable some of these generators from thermal sources, and then try to iteratively reduce or restore the load until the OPF becomes feasible, and compare the actual with the actual data to establish the benchmark. So to the best we can, it's not perfect, but to the best we can, we could see that the simulated load shedding as compared to the actual real load shedding, there is about 88% correlation coefficient. The noticeable difference is actually happening after the coldest period, which is on the afternoon of February 16th. It is likely caused by some delayed load restoration, even when maybe many of the generators are already back online, right? And the real load shedding for each weather zone with about 95% confidence interval also matches the simulation quite well. Generation composition matches really well. So this is step one, that is to establish an open synthetic grid and data so that not only us, but the researchers across the board could begin to simulate and try to analyze, to the best that we could, what happened during those periods. And then the next question is, of course, trying to figure out what are some of the corrective measures, like what could have been done differently to avoid disasters like what we had experienced last winter. So here we try to, based upon this model we developed, we try to compare 4 different corrective methods. And that's something that a lot of people were talking about in the news media and so on, but we try to do, we're trying to provide a bit of a quantitative grounds for that. One is winterization, and the other one is how about connecting Texas with either Eastern or Western interconnections. The third one is large-scale demand flexibilities. And the fourth one is maybe we should have some strategic energy storage facilities. So building upon the model we developed, one can begin to reason about their effectiveness. And here we utilize a commonly acceptable metric called energy not served as the metric to quantify the effectiveness of each scenario as far as reliability improvement is concerned, okay? So here are some results that we obtained during this exercise. And the one that you see on the top is that if you would like to have different level of energy storage, what would have been the level of a load shedding during those peak periods, right? So as you could see, with increasing level of energy storage, that could help. And then another figure you see on the bottom is that we begin to put several of these corrective measures together. Here, we're trying to put 3 different corrective measures all together and try to visualize what is their collective effect on reducing load shedding or energy not served. Here, you can see the x-axis is the HVDC connection capability, how much you want to connect Texas with the rest of Texas. And the y-axis is how much gigawatt of demand reduction or response you might be able to obtain. And then A, B, C, or you couldn't see C, but the three charts you see is winterization of 10 or 20 or 30 gigawatts of generation facilities. As you can see, combining all three of them, you could see a different effect on the energy not served reduction, meaning the more bright the bubble is, it means there's more reduction on energy not served, meaning we avoided more load shedding events, all right? And that could also be utilized to quantify what is their total collective impact on this on the power grid during those periods. So to summarize, we developed an open source extendable synthetic grid model that is building upon some of the earlier work by our colleagues here at Texas A&M. And then we hope that it could actually serve as a platform for the broader energy community. So perhaps not necessarily only for the power system engineers, but also for a lot of the broader energy and climate concerned research communities to begin to quantitatively assess the severity as well as corrective measures that happened in Texas in 2021. And then we tried to, as an example, articulated 4 types of corrective measures to analyze and establish the respective and combined effects on mitigating such events in the power outage. And then coming back to this pyramid chart I talked about at the beginning, this is sort of a attempt to influence using solid technological grounds to help the policymakers make some of their policy related decisions. And this was, I remember that at the onset of the outage night, I had a quick phone call with a few of our colleagues, and this is something we wrote and published on the February 16th of the Houston Chronicle as opinions page. Here's another one which I will just quickly share with you, not necessarily on the specific techniques, but just to try to show you that some of the things that we are thinking about when it comes to what could have been done differently. And this is a very recent news report from Austin. Let me just share that real quick. From KXAN. Please let me know if you cannot hear it.
Is looking at other kinds of smart technology.
You might be able to prioritize some of the more essential needs of the energy during those times.
The idea is, instead of shutting off power to entire areas to decrease demand during a crisis, what if we could remotely disable all of the less urgent energy needs, such as running dishwashers or your washer dryer, in order to keep more life-saving things powered on? That's things like your light and your heat, all using smart appliances.
That's exactly what many of the university researchers are working on these days, which is to leverage the power of better computers, better communication, and better control devices to scale up that.
Dr. Leger says the goal is stabilizing our grid's power supply and demand earlier and at a more granular level to prevent another compounding power crisis.
Until these kinds of solutions are possible, we can do.
So, I don't want to take too much of your time on this, but this is just some examples of some of the things that we might be able to help when it comes to better demand flexibility to avoid such outages in the future. So to summarize, I think this is really one of the most exciting time for us to be in the electricity sector, because we are the key infrastructure to enable any kind of a climate solutions. And I think significant research is needed to modernize the grid under those extreme conditions. And we just showed you some simple examples actually on how to build open, extendable, and data-driven approaches to shed some light on both technical as well as policy measures handling those extreme conditions. We welcome many of you to join us in efforts in developing those kind of models for extreme analysis, such as what is going to be the impact on carbon, what about cyber and physical security, and so on and so forth. So with that, I would like to stop and be happy to take any questions that you may have. Thank you.
Thank you so much. That was
Thank you.
wonderful. So much information and very insightful. So we only have a few minutes left. So any questions from the audience? Listening.
There's one in chat.
Yeah, so I see there's one question regarding the lagged variables in the VAR models. If I understand what you mean by lag variable, I guess you're talking about some kind of a time delayed responses, right? For example, some of the data that happen in time step K may affect electricity consumption in time step K+1 or K+2. So that is actually something one could incorporate in the VAR model analysis. In other words, it's not a snapshot analysis. It's rather a moving window analysis. We actually capture a sizable chunk of the window size to include those effects of lag variables. So that's actually a good feature of the VAR models.
So does the VAR model also work with like a social demographics variable, any kind of variables?
So VAR model actually started from social sciences community. It was used first to analyze the impact on macroeconomic activity. For example, if you want to understand the exchange rate, import, export from country 1 to country 2, and then you want to understand which one would have the most impact on the country's GDP growth, right? So that was actually when this whole model was pioneered by Professor Sims back in early 80s. So as long as it's a time series, and as long as those underlying variables are interdependent, the applicability is quite well. Yeah.
Okay, any other questions? So what's next? If no question, I'm going to ask. What's next?
Well,
Are you going to
next,
build more?
right, the next one, we are actually, I think one of our students is also sitting in the audience, and we might need your help, Chen Fei, which is, we're trying to understand how does, we have a lot of data at the macro level and intermediately level, but we have relatively little data on individual level. So we're thinking about you actually, of maybe you ask some help from social scientists or behavioral aspect experts to figure out how does this COVID thing affect individuals' behavior and therefore affect kind of a household energy consumption models, right? So for example, if I draw a load profile of a household, post-COVID versus prior to COVID, do we see any differences? Or could we actually draw such a profile? Could we have a composite model of household energy consumption based on the appliances of your households?
I see. I mean, mention this individual level and also like census tract level is a challenge, but I think we can think about a way to do it, and
especially at the individual household level.
Yeah.
And we are actually thinking about that as we speak. So
yeah, we can have a talk. I can share all
Okay.
the data I have.
okay, that'd be great. Yeah.
And then also my paper just published that data set can actually merge to your data set. I have 7 data set merged in that paper I just published. And that
Okay.
data set can merge to your data set, create more bigger data set.
Right. Yeah, that would be good.
Yeah. All right. Anything else? Dr. Tansovic say very interesting work.
Thank you, Kevin. Appreciate your joining. Yeah.
All right. Thank you so much.
Thank you.
Maybe I can have a 5-minute chat with you.
Sure. I'll stay on the
Okay.
Zoom call.
Yeah. Thank
Yeah.
you so much,
you
everybody.
all.
We
Thank you.
won't have class next week. Just let everybody know. Everybody have a break. I think it's next Friday. We have a recess. Okay, so 等一下. So I have 就是我这个I have this I think we can stop recording. I'll wait for Ryan to. Yeah, Ryan, we can stop recording.